Okay, so now we have got a statement of what the momentum principle is. If you know what the force is and how much time it acts, you get directly how the momentum changed. But that's not probably what you want to know. You may want to know where is the object and how is it going to hit somebody, or how can you aim an object launched from the Earth, get it to Mars, get it from Mars back to the Earth. If you want to be, and someone out there listening is going to be in the population of people who are going to get the first chance to be humans on Mars, you really want to know not just the momentum, but where is an object and when. You want to make sure you get back to the Earth's orbit when the Earth is where you're going to be. So this is the simplest possible case. We've got a constant interaction, and the constant interaction that's easiest, our very first constant interaction that we'll deal with is the weight. So we know what the weight of an object is. Its weight. It is a vector. Let's say that I've got an x direction, y direction going upwards, and z coming out. The weight has got a 0x component. It has minus w. So an object has a weight. You put it on a scale. You know what its weight is. That's the number that goes in the y component, 0 in the z component. That's what the weight of an object is. So there's my origin. Let's suppose that I start an object right here, so that the initial position of the object is equal to, well, it is, let's say that it is d in the x direction, it's 0 in the y direction, and it's 0 in the z direction. So there's the initial spot for the object. The final spot is after it's been allowed to be interacted with for this, by this weight interaction. So it has fallen some distance that I don't know yet. I'm going to call that h, is the distance that it's fallen. It has got some velocity that I do not know, v final. So the final position there, our final, if it's dropped from rest, it's going to be still d in the x direction. In the y direction, it will be minus h, and then 0. So that is, you see this all the time. You just drop your textbook, and you will hear it slam with some velocity v final after it has fallen a distance h. I want to know two things. How much time did this take? I know how far it's gone. I want to know how much time, and I want to know v final. Those are the two things that I want to know from this. Now, you might be tempted, if you've taken a physics class before, you might be tempted to say something like acceleration is equal to a constant, so x is equal to x0 plus v0, xt, y is equal to y0 plus v0 yt plus 1/2 ayt squared. And now you've got knowns and unknowns and solve the problem that way. That is a calculus way to solve the problem. It uses calculus ideas. It does not, I mean, the constancy of the acceleration here is not a fundamental idea. It's a result of fundamental ideas. So when you see a problem like this coming to you on a test, you're not to use this constant acceleration kinematic stuff. That is actually going to, I can easily ask a question that is going to wrap you around in algebraic circles that you will never come out. How can you approach this from our fundamental statements of the momentum principle? And here's how you do it. So I'm going to do this in our problem-solving format. The director says, I recognize this as a falling problem. This is a momentum principle problem with a constant interaction. So I need the momentum principle. I need the definition of the average velocity. That's the thing which takes me from my initial to my final. Here is what the average for this process looks like. The average times delta t. It's the thing that changes position, the same way the force is the thing that changes the momentum. And I'm going to need the position update idea. So those are the only three ideas I need. Three ideas. What do I know? I know r initial is equal to d, 0, 0. I know r final. I know how high this thing is over the ground. D minus h comes here. And I also know that the weight, let's suppose I know the weight of the object is equal to 0 minus w, 0, and let's say that I know the mass of the object, m. So I know what it is. It's a box, it's a block, something. What's unknown? I don't know delta t, but that's what I want to know. Delta t is one of the things I want to know, so it's a target. I'll circle it. I want to know what the v final is too. V final, circle it. Anything else I don't know? Well, I don't know what the v average is going to be. V average, which is 0, the average y 0. That is something I don't know. So there are, in fact, 3 unknowns in this problem, although the v average is not one that I stated. This is an implicit unknown. There are 3 unknowns here. And that is the director's level job. Now, the investigator. Okay, here I've got, it never hurts to redraw the sketch. Here's my origin. There's the x direction, the y direction, and the z direction coming out. Here is our initial, which is equal to d, 0, 0. Here's our final, which is equal to d minus h, 0. And there is this v final there. This takes some time delta t to do that. So there is my sketch. Each one of these is an idea I'm going to use. The momentum principle. Well, what does the momentum principle says? The final momentum of this object, m times v final, is equal to the initial momentum of this object. It starts from rest. Plus how much time goes by and the interaction. Delta t times the weight. And that is equation number 1. It involves a single unknown, 2 unknowns, sorry. It involves both the v final and the delta t. So we're not done with that problem. We don't have enough yet, as an investigator, to say, go ahead, execution, your job. Average velocity. Well, since the velocity is changing at a constant rate, the average velocity will always, in a problem like this, just be the algebraic average of whatever the initial velocity is and the final velocity. And I'm just going to leave it like that. You should as well. So there you go. I've got 2 equations now, but I added 1 unknown. I added the v average. So now I've got 3 unknowns for these 2 equations. So I'm not done yet. The last one that I've not used is the position update idea. So here's what position update says. My final position, which is d minus h, 0. That's the final vector position, is equal to the initial vector position, d, 0, 0, plus delta t times v average. And that is equation 3. I have not added any more unknowns, but I've added 1 more idea. So now I've got 3 equations and 3 unknowns. 3 equations, 3 unknowns. And I'm good to go. Go on to execution. Okay, executor. This is always going to work pretty much the same way. I have from statement number 1 that v final is equal to delta t times the weight divided by the mass. Right, I just divided both sides of that by the mass. Now I know we'll get to what the weight is as mg. But the weight, if I put g in there now, I don't want you thinking about gravity. I just want you thinking about the weight interaction. That's what the v final is. I'm going to substitute that into equation number 2. So the average is equal to 1/2 times the initial velocity is a known, 0. The final velocity I get from equation 1 plus delta t weight over m. So now the average velocity is known. I'm going to substitute that into equation number 3. So I get d minus h, 0 is equal to d, 0, 0 plus delta t times 1/2 times delta t weight over m. And, yep, that's exactly it. I've got a vector equation there. So now I've used all of the information that the investigator can give me. I'm going to say, let's resolve this into x components. The x components of this equation is d for this vector is equal to d for this vector plus the weight is the only vector here There's the weight, and the weight has got a 0x component, so I get 0. So in the x direction, I get d is equal to d, which is fine. That's exactly what's supposed to happen. Let's look at what the y says. I get minus h is equal to 0 plus delta t squared over 2 times, now the weight has got a y component of minus w, and then I divide by the mass. And now I've got just a single equation with delta t in it. I can tell you what the delta t is. So I get 2hm divided by the weight is equal to delta t squared. So delta t is equal to the square root 2h times the mass divided by the weight. And now if you look back at work we've done, we see what the V average here, equation number 1, if I knew what the delta t was, now I can back substitute and find out what the V final is. So I just take whatever my delta t is and multiply it by weight over m. So V final is equal to delta t times weight divided by m, which is the square root 2hm divided by weight times the weight vector divided by the mass. And that's what the V final is. So let's go a little farther. V final y is equal to square root 2hm divided by w. The y component of the weight is minus w, but then I divide by an m. There's the divided by m. So now I get minus the square root of 2h. The w is now going to go into the numerator, w divided by m. And here are now my answers. I've got delta t is that, and I've got v final y is that. I know how fast and now where. So, but I am not done yet. I see that we're already at 12 minutes, but we're not done until we have got the skeptical review. First thing is check the units of delta t. I have got the units of square root. The 2 doesn't have any units, so I'm not going to worry about that. The h is meter, the m is kilogram, and the weight is a newton, which is a kilogram meter per second squared. So if I cancel a meter from the numerator and the denominator, cancel those kilograms, I get the square root of 1 over second squared, which is the square root of second squared, which is seconds. So that's the first thing. And there are no unknowns. So delta t is looking at least like it could be right. Let's see about v final y. Its units are, look at the box. The minus and the square root of 2 don't have any units with them, so I don't need to keep track of that. The units of the square root of h is meters. W is now the newton. That's the kilogram meter per second squared. And then in the denominator, we've got kilograms. So those kilograms cancel. So I have the square root of meters squared per second squared, which is meters per second. So then that is a velocity. And now, and again, there are no unknowns. Now the behaviors. Look at the expressions here. Delta t increases if h increases. So if you fall farther, it takes more time. Which is good. Look at the expression for v final. Again, if h increases, then v final increases. You fall farther, you hit harder. This is 1 check, 2 check, and then the basic checks. And that is the solution that I want to see.